ఇంటర్మీడియట్ విద్యారంగంలో అగ్రగామి మన ఎన్ఎస్ఆర్ ఇంపల్స్ ఎడ్యుకేషన్ ఇన్స్టిట్యూషన్. ఐఐటి, జేఈఈ అయినా, నీట్ అయినా తిరుగులేని విద్యా సంస్థ ఎన్ఎస్ఆర్ ఇంపల్స్.
Hi everyone. So in the previous classes we discussed about the switching problems and common potential method, right? So now we will discuss one more problem based on the common potential method, then we can go for the next concept. So mostly we will complete the topics today, okay, right? So the question is, two parallel plate capacitors A and B of capacitance values C1 is 1 microfarad and C2 is 5 microfarad, okay, are charged separately to same potential 100 volts. So they have already initially charged to the same potential V 100 volts, okay. Now they are connected in such a way that they are connected such that positive plate of A is connected to negative plate of B. Then find charges on each capacitor and loss of energy. So this is the question, okay. So here there are two capacitors A and B, their capacitance value is also given, they are charged separately. For example, this is capacitor A whose capacitance value is 1 microfarad and capacitance B whose value is 5 microfarad, and they have been charged separately to the 100 volts. This also 100 volts. When the capacitance is given and voltage given, you can find out charge. Now what is the charge of first capacitor? Q is equal to CV formula. So the charge is equal to C is 1 and this is 100. So that 100 microcoulombs. Now so it is Q2. So again formula is Q2 is equal to CV. So Q2 is equal to charge is 5 micro into voltage is 100. So it will be Q2 which is equal to 500 microcoulombs. Means initially they have the charges, one is 100 micro, another is 500 micro. Now what they have done? Now they have connected such that positive plate of A is connected to the negative plate of B. Means I can say that this is capacitor A whose positive plate is this one and negative plate is connected to negative plate of the B. So positive plate, negative plate are connected to the common point, and this negative plate and positive plate are connected to the common point. And you know that when end points are connected to the same ends, the plate ends are connected to the same end point, they are connected in a parallel because their potential difference is 0. So you know that here I can take some small a and small b, and you know that they are connected in parallel. They are connected in parallel. So when it is parallel, there is a common potential which is constant for both of them. Okay na? Potential is constant. Okay. Now what is the total initial charges? This is 100 micro, this is 500. When they have connected in opposite like plus and minus, if you consider this as the nodal analysis, node, now for this node, this is plus, this is minus, means this is plus 100 microcoulombs, this is minus 500 microcoulombs. Now what will be the total charge? The total charge at node A, total charge is equal to, this is plus 100, this is minus 500, so that plus 100 microcoulombs minus 500 microcoulombs, so total charge will be minus 400 microcoulombs. Okay na? And I told you in the previous class common potential, that formula, how to find out common potential. V common is equal to charges Q net by charges by capacitances, means V equal to Q upon C. Q means total charge, here plus minus is connected, so that negative. And what is the capacitance equal? You know the formula, V is equal to Q net by C net, and when they are connected in parallel, formula will be C1 plus C2. This formula I told you, like C1 V1 minus C2 V2. Okay, here we got Q, no problem. So V common is equal to Q1 minus Q2, we got how much? Minus 400 microcoulombs by C1 plus C2. C1 is 1, this is 5, so 1 micro plus 5 micro, so it will be minus 400 by 6 will be minus 200 by 3, minus 200 by 3 volts. So we got the common potential. Now finally what are the charges? Now final charge, let me take Q1, small q1, which is equal to Q equal to C1V, because V common we know, Q formula is CV, so C1 into V. Now what is C1? C1 is 1 micro, C1 is 1 micro into voltage is minus 200 by 3. So you can say that it is minus 200 by 3 microcoulombs. So what is minus 200 by 3? It is nearly 66.7, minus 66.7. So you can say this is minus 66.7 microcoulombs. Now what is the charge Q2? Q2 is equal to C2 into V. C2 will be 5 micro into voltage is minus 200 by 3. So which one will be? Minus 1000 by 3. So that you can say minus 333.3 microcoulombs. See, you can add both of them so that you will get the same charge again. So what is the charge here? Minus 66 and here minus 333. Add both of them, you will get minus 400. So minus 400. So the total charge must be conserved. Here positive and negative is connected, that is why charges are nothing but Q1 minus Q2. If same polarities are connected, charges will be Q1 plus Q2. So this is how the charges are distributed after the common connection. Okay, now they are asking the charges. So this is done. What are the final charges? Minus 66.7 minus 333. And they are asking loss of energy. So what is loss of energy? Initially the capacitors have some energy with them, and finally the charges are different, so that there will be some loss of energies. Now loss of energy is nothing but initial energy minus final energy. So that loss of energy delta U I can find as, so loss of energy delta U is equal to initial internal energy minus final. So initially you can find out initially internal energy for the first capacitor, you know capacitance value and potential value, so that half C1 V1 square plus half C2 V2 square, so that half into C1 is how much? 1 micro, V1 is how much? 100 square, plus half into C2 how much? 5 micro, so that 100 square. So you can take half 100 square common, it will be 1 and 5, 6, so that half into 6 is 3, 3 into 100 square will be, so it can be written as 3 into micro means 10 power minus 6, 100 square will be 10 power 4, so you can say that 3 into 10 power minus 2, 3 into 10 power minus 2 joules. So this much energy initially is there, and finally again half C1 into, what is the common potential we got? Minus 200 by 3 for both of them. Half C1 into V common square plus half C2 into V common square. So that you can take again half VC square common. So that half into VC square how much? Minus 200 by 3 whole square into C1 plus C2 we got 1 plus 5, 6. So that half into, this is 4 into 10 power 4 by 9 into 6 microfarad, so that minus 6. Again you will get, so 2 1 2 2 and this is 3 2 3 3 so it will be 4 by 3 into 10 power minus 6. So minus 6 and 4 becomes minus 2 joules. Are 4 by 3 how much? So 3 1 3, again 1.33 into 10 power minus 2 joules. This is the final energy. So initial energy this much, final energy this much. So how much is the last? Initial minus final, 3 minus 1.33. So delta U will be, so delta U, which is initial energy minus final energy. Initial is 3 into 10 power minus 2 joules minus final is 1.33 into 10 power minus 2 joules. Automatically 3 minus 1.33 is 1.67 into 10 power minus 2 joules. This much energy is lost. So the energy lost may be in the form of a heat to the surroundings. You might know already. I have explained when the capacitor charging takes place. So some work will be done by the battery, and so that energy will be stored in the capacitors. Remaining energy will be lost in the form of heat, right? Okay. Then, did you understand the common potential method? Yes. Then we can go for the next one. How this graphical variations of the electric field and voltages or potentials in the cases of the dielectrics. Graphical variations, graphs of electric field and distance and potential and distance in the case of dielectrics. The case of dielectrics kept in between the plates. For example, see, there is a parallel plate capacitor of the distance, let it be d, and it is of high potential, plus charge is given, it is minus charge is given. You know that electric field is always from plus to minus of value E. You can say E naught because it is air. Now in between the plates, in between these plates, I am connecting, I just connected or kept some dielectric mediums. So see here, I kept some dielectric of value K. What is the dielectric constant value? K. And this thickness is, let me take T, and this is X and this is Y. This distance is Y, this distance is X. Now, so what is this? This is dielectric. And we already know that dielectric can reduce the field. Dielectric material will reduce the field due to polarization, right? So that we know that inside dielectric, the net electric field always decreases by k times. This is E naught, means in the air, decreases by k times. So how the graph will be drawn? See, from here to here, this is air and electric field is constant, so that here electric field will be E naught, and after in this material electric field value decreases to k times, and again in the air electric field will be same. So I can draw the graph between electric field versus the distance. See, up to this one, this is the distance x, and this is the t, and this is the y, the total distance is d. I can say that up to x distance this is air field. So this is air or vacuum. So that electric field will be E naught. Electric field will be E naught. So up to the distance x, electric field will be constant, which is equal to E naught. Now in this T, dielectric is kept. We know that dielectric reduces the field, which is by k times. So I am taking electric field somewhere down because it decreases. What is this value? E naught by k. What is this value? E naught by k. And after again, when the air comes, again it will go to the same. Again it will go to the same electric field. So electric field inside the dielectric is less than the air. So air in the air, electric field is more. So this is what electric field. Now what is the graph for potential? What is the graph for potential versus displacement? Okay na? Now you know that when electric field is going, you know electric field always go in the direction of decreasing potential. And here electric field, you know the formula, V is equal to ED, electric field into D. The potential difference is equal to electric field into D. You know that electric field is constant. Now potential difference directly proportional to displacement. It must be a straight line. But you know that it is dropped, so that the straight line might be like this because potential drops. Now let me take here some voltage is 20 volts and here will be 0 volts. Now, so how the potential is dropping? See, up to the x distance it is air only, so that simply delta V is equal to air electric field into D, so that it might be dropped from 20 volts to some volts like this. So voltage is dropping. Okay na? Now in the dielectric, when comes to the T inside the dielectric, so we know that this is delta V is equal to E naught into D up to this case. Now in the dielectric, you know that delta V is equal to E naught by k times D, because in the dielectric electric field decreases, so that here this D by k value is less, so that it cannot change that much fastly, it can change somewhat slowly. So the slope will be less, so that if it is changing very fastly, then it can change, it cannot change that much fastly, it can change up to like this. So if it is entire thing is air, it will change in a same manner, but it is medium, so that it cannot change like this, it can change like this. And after this the distance is y. Now it can again changes to 0, so it might comes to 0 because the final voltage we are taking is 0. Here what is the simple thing you need to observe? Potential will drop in the direction of electric field. If it is air, very fastly decreases. If it is any dielectric medium kept, not that much fastly, slowly decreases, but decreases. Okay na? So this is the variation of the electric field and potential with respect to distance when some dielectrics are kept. So you can see lot of questions are given in our material, so that you can analyze the graphical variations for number of dielectrics kept. So simple funda here is, if it is a air, electric field is E naught. If it is a dielectric, electric field drops to E by k value. If it is a voltage case, voltage will decrease or potential will drop very fastly in the case of air. If it is a dielectric, not that much fastly, slowly. Okay, this is what dielectric. Sir, if I keep metal conductor, then what happens? If I keep in this case metal conductor, so here I am just going to explain you the variation of the electric field versus, this is capacitor, plus q and minus q, the distance is d. Now here I am keeping some dielectric, this is what dielectric, and here I am taking one more material, but this is called as conductor. For a conductor, what is the k value? Infinity. This is conductor. And you know that in a conductor electric field is 0. Inside the conductor electric field is 0. When electric field is 0 means if it is the conductor, this electric field inside is 0. It means that here the potential is V, then here also potential is V, because there is no potential difference. If the potential difference is there, then electric field exists. If the potential difference is not there, electric field is 0. That is the main thing here. Now I am drawing the electric field versus distance first. So this is electric field versus distance, and here potential versus distance. Okay, now first electric field, up to here it is air only, so that electric field is maximum. This is E naught. So up to the distance x, and after you got a dielectric, so that electric field will be reduced, so which is E naught upon k. So up to this distance. Now after that we got a air again, so again it will go to the maximum. So this is E naught, and after this we got a conductor. Inside the conductor electric field is 0. Electric field is 0 because it is conductor. And after that again air we got. So in the air the electric field is. So this is the graph for electric field versus distance. See, in the air cases all electric fields are maximum E naught. Whereas in the dielectric case, electric field is decreased by k times, whereas in the conductor electric field is 0. Now if I draw the same graph for potential, see here initial potential I can take it as a 20 volts. Now in the air the potential will be decreases. So I am just drawing like this, so that no confusion. Okay, so initially it is the air, so that very fastly the potential decreases, and in the dielectric it can drop, so that it cannot drop that much fastly. If it is the entire air, potential drop like this, but now it cannot drop like this. So in dielectric very slowly the potential drops. Next, now you got air, so that again drops very fastly. Now coming to the conductor, this is conductor region. You know that in conductor potential difference is 0, means potential is constant. So potential difference is 0 means delta V is 0, means potential is constant, means the potential will be constant. So here V is constant. Now again air comes, so that it can drop to 0. So this is the graph for electric field versus potential for dielectrics and conductors placed in between the two parallel plate capacitor. Okay, did you understand? Now, so with this the topics are completed. We may extend this capacitors to some far, but so I would like to conclude this theory here. So we will do more problems. So in the beginning, I have discussed you the spherical capacitors. Spherical capacitor. So this is one type of the capacitor. We have three types of capacitors. One is parallel plate capacitor. So far we are discussing parallel plate. The second one is spherical capacitor. Third one is conducting, that's hollow cylindrical capacitors. Now we are discussing spherical, and I am keeping two spheres. So hollow spheres I am taking, hollow spheres of first radius is R1 and another sphere of radius R2 I am taking. Okay now, and you know that for this spherical capacitor there is a capacitance. What is capacitance formula? Q upon the potential difference. This is how to find out. And you can say that the capacitor, this is A, and this is B, this is A. Now we are giving some charge like this from this, so that this is plus Q and this is minus Q, because loss of charge will be negative. Okay, this plus Q is given here, it means this is negative. Okay, right. Now we are just finding the potential difference at the this point, first plate and second plate, and that delta V is nothing but potential at 1 minus potential at 2, and we did this method and we got the capacitance formula as 4 pi epsilon naught R1 into R2 by R2 minus R1. This formula we got at the beginning. So this is what capacitance, spherical capacitance, okay, now 4 pi epsilon naught R1 R2 by R2 minus R1. Now sir, for a isolated sphere, sir, what do you mean by isolated? Isolated means if you take this one and this, bring this, or you just take this one, this second sphere to somewhere infinity, so that we left with only one sphere of radius R1. Now for this we are taking R2 at infinity, R2 somewhere infinity. Now for that, what is the capacitance? 4 pi epsilon naught, 4 pi not infinity, you can say R2 is very more than R1, not infinity, more than R1. So in that case 4 pi epsilon naught R1 R2 by, here R2 is more, so that R2 minus R1 will be written as only R2, because this difference is nearly R2. So cancel this, and capacitance formula we will get as 4 pi epsilon naught R1. So you can say that capacitance depends directly on radius. If bigger the radius, more will be its capacitance, so that more charge will be hold by it. Okay now. So this is what we discussed initially. Now sir, if they give you more number of this spherical shells, how to get the capacitance values? Okay na. So they have not given just a two. So there are 3 spherical shells, A, B and one more, C. How to find out? Here also you can just take 2 points from where charge was given, so it is plus Q and it is minus Q, and find the potential drops, and again C equal to charge upon volume, charge upon potential, you can get the capacitance value. Now sir, in some cases for this spherical capacitor, they might say like this: the first shell is earthed, or inner shell is earthed, or outer shell is earthed. Earthing means giving connection is given to the earth, means making the potential is 0. Earthing means what is the potential? 0. So if you do like that, what will be the values? For this one, if outer shell is earthed, and inner shell is given charge, So like this is inner of radius R1 and outer of radius R2 was taken, and what I am saying, outer one is earthed, whereas inner one is given a charge. Who will give the charge? This plate only give the charge, means this will be plus Q and this will be minus Q. If some charge Q is given, automatically this will be minus Q. So I can say that this surface is minus Q. Now how to find out the potential? How to find out the capacitance? The C formula, Q upon delta V. So delta V is what? If you take, this is the first point 1 and this is second point, delta V is nothing but V1 minus V2, and you know that at this second point already it is connected to ground, earthing. So V2 will be 0 because it is earthed. So whenever you can take the connection is to the ground, you can say that it is earthed. And what is the potential one? So you know from the electrostatics for a spherical shells, spherical shells, the potential inside will also be equal to potential on the surface, which is 1 by 4 pi epsilon naught charge upon capital R. For outside, 1 by 4 pi epsilon naught q by small r. So you know, right, potential is same. Okay, now I use the same thing. Now I want potential at this first point, which is nothing but potential due to the sphere itself plus potential due to second one, potential due to second one, right? So V at the first point is equal to, what is the potential due to the sphere itself? So it is nothing but the point is on the surface, the point 1 is on the surface. For on the surface, what is the formula? 1 by 4 pi epsilon naught charge by capital R. So 1 by 4 pi epsilon naught charge is q by radius is, you can take R1, plus what is the potential due to second one? See, second surface has minus charge, minus q. Okay, now this, due to this minus q, we are finding at a point 1. For this minus q surface, the point is inside, and you know that at inside or on the surface potential is same. So that 1 by 4 pi epsilon naught, the charge is minus q, and what is the surface? You don't see the point, surface. So that surface radius is R2. So here q by 4 pi epsilon naught is taken out common. So it is 1 by R1 minus 1 by R2. This is V1 you got, which can be adjusted like this. This is q by 4 pi epsilon naught. So R2 minus R1 by R1 R2. So when you got the V2 in of 0, so delta V will be V1 only. And what is the capacitance of the circuit now? That capacitor, spherical capacitance now, C is equal to charge upon delta V. So charge upon, what is delta V we got? Q by 4 pi epsilon naught into R2 minus R1 by R1 into R2. So Q cancels, this will go up, so that it will be 4 pi epsilon naught R1 R2 by R2 minus R1. So this is the capacitance when inner sphere is given charge q and outer sphere is given earthed. Outer sphere is earthed, inner one is given charge. Okay, now we will see the converse, ulta. Now outer sphere will be given charge and inner sphere will be earthed. Then what happens? What will be the capacitance? Okay, na? So here the second one, outer sphere, outer shell is given charge, inner is earthed, inner is earthed. Now in this case, see here, so this is inside of radius, you can take R1 and outer surface as R2. So what I am saying, outer is given a charge, inner is earthed. So inner you can just earth it. Outer will be given charge. Or who will give the charge to the outer? Inner only give the charge. Means for inner we are just giving a charge q, so that this will be minus q. Okay, na? Now again for this system they are asking to find out the capacitance. Capacitance formula q by delta V. So delta V we need to find. This is 0.1, I can say this is 0.2 because this is plus charge, so high potential. So it is nothing but q upon V1 minus V2 again. That is again you need to find out like finding potential at V first point and finding potential at second point. And see this second surface is already earthed. So that can I say V2 is 0 because it is earthed. So we need to find out only V1, then it is enough. Okay. Then, so when the inner surface is earthed, now what will be the potential at the 1? Okay, na? So we need to find V1, V at the first point. V at the first point, potential at the first point is because of this sphere and this sphere. Okay, na? So you can say that potential due to this sphere of A plus potential due to the B. Potential due to first sphere A and second sphere B. What is the charge on the first one. So it is minus q because we have given. But you know that, see, we have given a charge so that it is minus q, then after we earthed means after connection of the earthing there may be some charge distributions. See, simple point here, we have given a charge q, means from this inner shell we have taken some charge and given, so that this will be plus q, this will be minus q. Now we earthed. Because of earth what earth will do? Earth will always wants to make the potential of the surface 0. Means here already minus q is there, so that it will give some charge, tries to give some charge, so that it will nullify the potential to 0. Means that initially the condition what they given, the inner shell is earthed, means V2 is 0. So that what I will take is inner shell having some charge q dash, means after finally the distribution, after the that grounding, q dash is the charge. Okay na? Now outer shell already you know that it is plus q. Now we are going to find out potential at 2, that is because of this surface, first surface, and because of the second. Now what is the because of the first one at this point 2? So that is because of its own, so which is nothing but V2 already 0 is equal to due to own k into charge is q dash by what is the distance r1 plus what is due to b. For the b point is inside, so for inside points are surface potential is same, so that k into q by what is the surface distance radius r2. So you can say that from here you can say that bring this kq by r to this side, so kq dash by r1 which is equal to minus kq by r2. So kk cancels, we will get q dash as minus r1 by r2 times q. This is the charge on the inner surface now. Now due to this you find out the potential now, then you will get the answer. See here the charge of the inner is already now q dash, the charge on the outer is q. Now we want potential at this point 1, V1 because of the inner sphere, because of the outer sphere. So V1 is equal to, because of the inner sphere we need to find out this at this point. So for the inner sphere the finding point is outside. So formula will be kq by small r. So k into charge is q dash by small r is nothing but this distance, right? So this is r2 plus Vb due to the own sphere k into q by r2. So V1 is equal to, what is q dash? You got already. So k into minus r1 by r2 into charge by r2 plus kq by r2. So here kq by r2 you can write this one as kq, you can take it out. Now you will get minus r1 by r2 square plus 1 by r2. See here multiply r2 divide r2, so that LCM will be r2 square, so that V1 will be kq into this is minus r1 and plus r2 by r2 square. Now you want to find out the capacitance, charge upon voltage, potential V1 only, because second surface is already V to 0. So charge by this is kq, what is kq? 1 by 4 pi epsilon naught q into r2 minus r1 by r2 square. So q cancels. Now capacitance of this system will be 4 pi epsilon naught r2 square by r2 minus r1. This is the capacitance of the spherical capacitor when inside is earthed and outside is given a charge. Okay na, this is the difference. Sir, if you have taken cylindrical capacitor, then what happens? For a cylindrical capacitors, So cylindrical capacitor, again you need to take two cylinders, cylindrical capacitor. Again you can take a cylinder of, this is an axis of inner radius R1 and surrounded by one more cylinder. Okay na, this is R2. Now you give the charge from the outer to inner, so that inner will be plus Q, outer will be minus Q. This forms a cylindrical capacitor system. Now for this one, how to find out the capacitance? Again formula, C is equal to charge given is Q upon delta V. So charge given is Q upon delta V is nothing but, if this is the first point, this is the second point, so V1 minus V2. The same formula for finding capacitance, C is equal to Q upon the V1 minus V2. And you know from the electrostatics, due to this cylinder or a rod, electric field at a point P is already electric field due to the rod or a cylinder lambda by 2 pi epsilon naught R. Okay, now you want to find out the potential. You know the relation from electrostatics, delta V is equal to minus integration of E bar dot dr bar. So do this integration. So delta V is equal to minus integration of lambda by 2 pi epsilon naught R into dr. Sir, what is lambda? Charge density. Lambda is equal to charge upon length, charge upon length. If you do this one by the limits R1 to R2, okay na, so you will get the voltage, the potential difference, and again finding the capacitance, C is equal to charge by delta V. So finally you will get the formula as 2 pi epsilon naught L by ln R2 by R1. So this is the formula of the cylindrical capacitor. This thing you do as a homework, how to find out the integration, you know already. So for the this everything is constant except R. So 1 by R, integration of 1 by R is ln. Okay na, so do the method, you will get the answer. So this is what for the cylindrical capacitors. Okay na, so in the entire capacitance chapter, what we have discussed, what is the capacitance, holding the charge, and capacitance, how to find out by the formula C is equal to Q upon delta V, and after that types of capacitors, then parallel plate capacitors of area A and distance is D. What is the capacitance formula we got? Epsilon naught A by D, and after that finding the series and parallel combinations equivalent capacitance for total number of some given capacitors. So we have discussed some methods of Wheatstone bridge and symmetrical problems, and we have given procedure to find out the equivalent capacitance for any type of circuits by applying Kirchhoff's junction law and Kirchhoff's loop law. So after that we went for the force between the parallel plates and energy stored in the capacitors, energy stored and heat lost. Okay na. Then after we discussed the electric field and potential variations when dielectric is kept, and one more thing, that when battery is connected, keeping inserting dielectric, what happens to the all the parameters. Battery is disconnected, by keeping the and removing and connecting the dielectric, what happens to the all the parameters we discussed. Now we will see some problems, more number of problems, so which already given previously. Okay na, so some problems we will discuss.